In the last video, we talked about the probability that one event or another event occurs. Now we're going to talk about the probability that one event and another event occurs. So when we talked about or, we're talking about one occurrence and one combination of outcomes versus another combination of outcomes based on that one occurrence and that one trial of our experiment. When we talk about one event and another, we're assuming that both have happened, but we're assuming that they've happened in sequence. So probably a better way to say it is, what's the probability of one event occurring and then another event occurring? In other words, they're both happening and they're happening in sequence. So one event occurs and then the other event occurs. Now, when we talked about one probability or another probability, we use the term mutually exclusive to describe special situations. So if one event and the other can occur at the same time, if we're looking at one event or the other, but it's possible that both happen at the same time, then we say those events are not mutually exclusive. Essentially what we're looking at is the sample space, and we're looking at the combination of outcomes representing each event in question. If some outcomes represent the occurrence of both events at the same time, so for instance, maybe picking an even number and picking a number that's less than 10, something like that. It's possible to pick both an even number and a number that's less than 10. So those events are not mutually exclusive. If we wanted to pick a number that's even or a number that's odd, those events are mutually exclusive. We can't have a number that's both even and odd at the same time. So making that comparison and making that determination is important when we're determining whether or not one event or another occurs and the probability of that particular combination. Now, when we're talking about one event and another event occurring in sequence, the corresponding term that we're interested in is independence. So two events are said to be independent of each other if the occurrence of one has no effect on the probability of the occurrence of the other. In other words, we're looking at event A and then event B happening in sequence. If the likelihood of A, in other words, if A occurs versus A not occurring, sometimes that can have effect on whether or not the second event occurs. Sometimes it doesn't have an effect, sometimes it does. Whether or not it does determines whether or not the two events are independent. So sometimes if A occurs, it can either make B more likely to occur, or it can make B less likely to occur. If the first event occurring affects how likely the second event is, then we would say that the events are dependent. One has an effect on the other. If one occurring has no effect on whether or not the second event occurs, then we would say that they are independent. So as with the issue of mutual exclusivity, depending on which situation we fall into, our formula for calculating probability will change in order to deal with those special situations. So we're going to start with events that are independent. In other words, event A has occurred and then event B has occurred, but one occurring and then the other occurring, they have no impact on one another. So whether or not the first event happens doesn't affect whether or not the second event happens. So if our two events are said to be independent, then the probability that both A and B, or if you want to think of it as A and then B, the probability that that sequence of events will occur is defined as the probability of A and B, and it's going to be the product of the probabilities. So the product of the probability of A times the probability of B. And we can use this formula for any number of consecutive events. So maybe we're looking at a sequence of 5 events, A and then B and then C, then D, then E. The formula works in the same way. As long as all of the events are independent of one another, we just multiply their individual probabilities together, and that's going to give us the probability that the sequence of events happens. So here's an example, and we're going to have to determine, as with mutual exclusivity, we're going to have to determine whether or not our events are independent before we actually solve the probability problem. Okay, so let's look at a gambling situation. So a US roulette wheel has 38 numbered slots, so they're numbered 1 to 36, and then there's a 0 and a double 0. Of the 38 compartments, 18 are black, 18 are red, so those are going to be the numbers from 1 to 36, and then 2 are green. Those are going to be the 0 and the double 0. So gameplay has the dealer spinning the wheel and then releasing a small ball in opposite directions. So we spin the wheel one way and then we throw the ball in the opposite way. So as the ball slows to a stop, it can land in any slot with equal probability. So all the slots are sized the same, the wheel is balanced. It's just as likely to land in any one particular slot as any other. We want to find the probability of red occurring on 2 consecutive plays. So in other words, we want to find the probability of getting a red and then getting another red. So that word "and" tells us that we're looking at this situation. So it's red one time and then red a second time. We need to determine first off if these 2 events are independent. In other words, does getting a red the first time impact whether or not you get a red the second time? Well, some people would say that it does. That is superstition. Realistically, that's superstition. So in gambling type games, at least in games where we're not talking about cards, we're not dealing out of the deck and then not re-adding cards to the deck, in those situations, probabilities do change based on what happens. But a game like roulette, where the wheel never changes and we just throw the ball and we take the same sequence of actions every time, every spin is independent of every other spin. In other words, whether or not you get a red right now has nothing to do with the color you get the next time. Those events are independent. You can get a whole sequence of reds, you can get a whole sequence of blacks, you can alternate, you could get green the whole time. It's probably not very likely, just because it's less likely each time to get one of the green slots, but it's possible. One color occurring on one spin has nothing to do with the color that you get on the next spin. So these 2 events are said to be independent. That means that the probability of getting a red the first time and then a red the second time is going to be the probability of each of those individual events happening. So what's the probability that we get a red? Well, again, we have to think about the definition of probability. How many ways are there to get a red, and how many total possibilities are there? Well, there's 18 reds, so if we spin the wheel and get a red, there's 18 ways to land on something that's red, out of the 38 total slots that we could fall into, some of which are red, some of which are black, and 2 of which are green. So 18 out of 38 is the probability that we get a red. Now the second red, remember, that's equally likely. The fact that we got the red the first time has nothing to do with whether or not we get a red the second time. So the second probability is also going to be 18 over 38. So we have 18 over 38 times 18 over 38. We're not adding the 2 fractions together, we're multiplying them. Now when you add 2 fractions or you subtract 2 fractions, you want to have the same denominator, and then you're just going to combine the numerators together and put them over that common denominator. When we're multiplying fractions, we multiply both of the numerators straight across, and then we multiply both of the denominators straight across. We can, of course, reduce the fractions first if we want, but that's not officially necessary. We can multiply and then just reduce at the end. So if we do this in the calculator, let's do this with the non-reduced fractions, just to show you that your calculator will reduce it for you. So our first probability is going to be 18 over 38 times our second probability, which is also 18 over 38. And that's going to give us 81 out of 361. That's our probability. And if we want that as a decimal, which may be a little bit more meaningful, treat that as an actual division problem. So 81 divided by 361 is going to give us roughly 0.22. So in other words, about 22% of the time, this will be the sequence of spins you get. So it's more likely potentially to alternate, or maybe not. Maybe it's equally likely either way. Think about it this way. So let's take one step further. Think about what's the probability to get a red and then a black. Well, getting a red the first time has no impact on whether you get black the second time. So the probability of red is 18 out of 38. What if the second event we're spinning and getting a black? Well, how many ways can you get a black? Well, there's 18 black spaces out of the 38. So the probability of then getting black is also the same. So the problem actually doesn't change. So red and then red, red and then black, same probability. Black and black, or black and red, same probabilities. That's because all of these events are equally likely and they don't have any impact on one another. So the probability of any one sequence versus any other, as long as we're talking about red and black, where both are equally likely, all of those probabilities are going to be the same regardless, because again, those events are independent. Okay, let's look at another example. So one family happened to have 9 babies, all of whom were girls. Find the probability of this occurrence. Now we're going to assume that it's 50-50 that you get a boy or that you get a girl. That may not be true in real life depending on the parents and genetics and a lot of different factors. But otherwise, we can assume that getting a girl is just as likely as getting a boy. Well, this family had 9 babies and all of the babies were girls. How likely is it that we end up with 9 girls? So think of this as one event is getting a girl, and then another girl, and then another girl 9 times. So we're looking at a sequence of 9 events. Each of those is getting a girl. So if we were to take the individual events and we want the probability of the whole sequence, it's going to be the product of the probabilities of each of the individual events. Because one baby's gender is independent of the next baby's gender, all we have to do is multiply those probabilities together, and that's going to give us the probability of that whole sequence. So the probability that we get 9 girls, girl, 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 so on and so forth, 9 times, is the probability that we get a girl multiplied by itself 9 times. A cleaner way to say that is with an exponent. So taking the same thing and multiplying it by itself 9 times would be the same thing as taking that number and raising it to the 9th power. That's just an easier way to write down the probability so that it's a little bit easier to put into your calculator. And that's because, again, we're looking at the same event occurring in sequence. So the probability of each individual occurrence of that event is going to be the same as any other occurrence. So what is the probability that we get a girl? Well, all other things aside, you have a 50-50 chance of getting a boy or a girl. So there's one way to get a girl per birth out of the 2 possibilities, getting a boy, getting a girl. So the probability of each girl is going to be 1/2. Well, we're getting a girl 9 times. So 1/2 probability for the first girl times the 1/2 probability for the second girl, so on and so forth 9 times. So 1/2 to the 9th power is another way of saying that. How would you type that into the calculator? I recommend putting parentheses around the fraction. So put parentheses around it. So parentheses. The reason we do that is because then when we apply the exponent, your calculator very much understands that we're applying the exponent to the whole fraction. If you don't put parentheses, your calculator may interpret the exponent in a different way. Instead of applying it to the fraction, it may apply it to only the numerator or denominator. So the parentheses will just help your calculator to understand exactly what you want. So we're taking 1/2, up arrow means exponent, so raised to the 9th power. And that's going to be 1 out of 512. As a decimal, 1 divided by 512 is going to be about 0.002. So that's tenths, hundredths, thousandths. So that's less than 1% of the time. So about every 2, so tenths, hundredths, thousandths. About every 2 out of 1,000 times, you end up with a family with 9 girls. Now, as with the situation with roulette, what about any other occurrence? So what if we had, 5 girls and then 4 boys? Or what if it was girl, boy, 9 times, something like that? Does the probability change? The answer is no, because remember, any other event is just as likely as any other. A girl is as likely as a boy, and whether or not we get a girl the first time has nothing to do with whether or not we get a boy the next time, or vice versa. Any sequence is just as likely as any other, and the probability of each occurrence is the same. So the probability each time that you get a girl versus a boy is always going to be 1/2. So changing the sequence here doesn't actually change the probability. What makes the probability so low? What makes the probability so low is the fact that we have a family with 9 babies. It's the fact that we took this probability and we multiplied it by itself 9 times. If we only had a family with 2 kids, the probability of getting any particular sequence wouldn't be so low. Even 3 wouldn't be as bad, but the fact that we have 9 kids in this family automatically means that any particular combination is especially unlikely. But it's not the particular sequence, it's just the fact that there are 9 kids and we're looking at the probability for any particular sequence within a family of 9 kids. So just something to keep in mind. It may not be that particular sequence. You may immediately think, well, all girls, that seems really unlikely, versus alternating, which maybe seems more likely. In terms of actual defined probability, all girls and alternating gender is just as likely. It's not the gender that has the effect on the probability. It's the fact that this family has so many kids, and so we're taking a long sequence of probabilities. Okay, let's look at another example. So according to the National Hurricane Center, the probability that South Florida will be hit by a Category 1 hurricane or higher in any single year is 5 out of 19, or approximately 0.263. So that's the probability that we have a hurricane, maybe a hurricane that's named something like that, in this particular location per year. Okay. First question, what is the probability that South Florida will be hit by a hurricane in 3 consecutive years? Round to 3 decimal places. In other words, what's the probability that we get a hurricane that first year, and then a hurricane the second year, and then a hurricane the third year? What's the likelihood that we have that sequence based on this probability? Well, again, we have to ask ourselves the question, each of these events in the sequence, are they independent or are they dependent on one another? In other words, does having a hurricane in one year affect whether or not we have a hurricane in the other year? Well, in the absence of any information, we have to assume no. If we have a hurricane this year, we're probably equally as likely to have a hurricane the following year. We're not making any claims about whatever type of tropical depression we might be in. If there's any type of El Nino or La Nina kind of situation, we're not talking about anything like that. All we're saying is that the probability year to year is 0.263, and that's the probability for every year. So one particular event occurring versus the other, 1 year's worth of hurricanes has nothing to do with whether or not the next year has any hurricanes. So that means the probability of each of these 3 events is the same. So Hurricane 1 has no effect on Hurricane 2, how likely or unlikely it is, and then same thing for Hurricane 3. Now also, because we're looking at 3 years of the same event, the probability for each event is going to be the same. So probability of Hurricane 1 is going to be 0.263. Hurricane 2, same probability. Hurricane 3, same probability. So we're taking the product of those 3 probabilities, which is the same thing as taking that probability, which is common to all 3, and then cubing it. So the probability of a hurricane is 0.263, or exactly 5 out of 19 in this case, and then we're cubing that. So what does that look like in the calculator? So remember, parentheses around your fraction. So 5 out of 19. Let's see, delete, arrow over, close your parentheses, and then we're raising that to the 3rd power. Now, if we wanted to convert that to a fraction to make it a little nicer, F to D, there's your option for converting it, and it's in green, so second, and then that button says take that fraction, convert it to a decimal. In this case, we can't do it because it's saying that this particular number just doesn't really convert to a fraction. So that's our decimal form, approximately 0.018. In other words, it's about 2% of the time, based on this particular number, we can say that we would have 3 consecutive years of hurricanes. Now let's look at another question based on this situation. So what is the probability that South Florida will not be hit by a hurricane in the next 10 years? Okay, so in other words, for 10 years, we want to know how likely it is that we have a sequence of 10 years with no hurricanes. Well, again, we need to think about the events. So each event is no hurricane, and then no hurricane, and then no hurricane, 10 times. Does one event affect the other? Well, if having a hurricane has no effect on the next year's hurricanes or lack thereof, not having a hurricane, same effect. It doesn't affect whether or not we have another hurricane. Well, what's the probability that we don't have a hurricane for 1 year? If we know the probability that we do, then remember the probability that we don't, that's called the complementary event. If the probability that we do have a hurricane is 5 out of 19, then the probability that we don't have a hurricane is going to be 1 minus that number, which is going to be 14 out of 19. So our question is, based on this likelihood per year, this is how likely per year no hurricane is, what's the probability that we have a sequence of 10 years with no hurricanes? Well, remember, 1 year's occurrence or lack thereof is not influential on whether or not the next year or the next sequence of years ends up in hurricanes. So it's the probability of our first non-hurricane year times the probability of the next year times the probability of the next for 10 years. So it's the probability that we have no hurricane, which is 14 out of 19, raised to the 10th power, which just means take that and multiply it by itself 10 times for each of those 10 years in the sequence. So 14 out of 19 to the 10th power, again, you can do that in your calculator, that's approximately 0.047. In other words, about 5% of the time we'll go a whole 10 years without a hurricane. Okay. So those are a few examples of events that are independent of one another. Whether or not one happens has no impact on whether or not the next happens. In those cases, we're looking at equally likely events in most cases. We're looking at theoretical probability, where we can calculate one event easily and one event versus the another occurring in sequence. One has no impact on the other. Now, what happens if that's not the case? So two events are dependent if the occurrence of one has some effect. It can have differing effects, but it has some effect on the probability of the occurrence of the other. So we're talking about a sequence of events, so A occurring and then B occurring. If whether or not A occurs either increases or decreases the likelihood of B, then that means A has an effect on B. It could go either way. It could increase the probability of the next event. It could decrease the probability of the next event. We're not really sure. It can vary from situation to situation. But the fact that the first event changes how likely the second event is to occur tells us that two events are dependent. One is dependent on the other. And if we flipped the sequence, one would be dependent on the other and then vice versa. So flipping the events doesn't change whether or not one is independent of the other or whether or not they're both dependent events. So if the two events impact one another in terms of the likelihood of each occurring, then we say these events are dependent. So again, we have to adjust our probability formula. So if our events are dependent, then the probability that both A and B will occur, in other words, A and then B, is going to be the probability of the first event, no changes needed. So the probability of the first event is just the probability of the first event. We're then going to multiply by the probability of the second event, but we're going to take that probability based on the fact that A has already occurred. In other words, we have to reanalyze the situation based on the fact that we're assuming that the first event occurred. What impact does that have on the situation as a whole? And we have to analyze how that affects the probability of the second event. Once we can put this into context, it'll make more sense. But what we call this is called conditional probability. So we're taking the probability of B conditional on the fact that one other event has already occurred and somehow one event affects the other. We'll put this into context. And then as with independent events, we can use this formula for any number of consecutive events regardless. So we could use this for a sequence of 5 events as long as we take into account that each sequence of events affects the next event if we're considering these to be dependent events. Okay, so for example, a box of chocolates contains 20 pieces that look exactly the same. In other words, in terms of drawing chocolates out of the box, if you were to pick one, you don't know which one is which necessarily. They all look the same. However, out of the 20 pieces, 5 are chocolate covered caramels, and then the others are just some other type of candy. We don't know what they are. We want to find the probability that you'll choose 2 caramels in a row. In other words, caramel 1, choose your first draw as a caramel, and your second draw is a chocolate covered caramel as well. Now, why are these events dependent? Well, think about the situation described. So we've got a finite box of chocolates. The box of chocolates only has 20 pieces in it. Why are the 2 draws dependent? Well, think about what's happening. So the first time you draw, you're pulling out a candy, and in this case, we're looking at the first draw being a caramel, a chocolate covered caramel. So we draw a caramel out of the box. That's the event that occurs first. Why does that affect the next event? Well, number 1, it affects the next event because now there's fewer chocolates in the box. So whether or not we draw a caramel the first time immediately affects the fact that there's now not 20 candies in the box. Once we draw one, there's only 19 candies in the box. But more importantly, the fact that we draw a caramel the first time now means that we have fewer caramels to draw from the second time. So if we draw a caramel the first time, there were 5 caramels to draw from out of 20. So the probability of drawing a caramel the first time is going to be 5 out of 20, because there's 5 ways to do that, out of the 20 pieces of candy in the box. But the second caramel, if we draw a caramel the first time, then there's only 4 left to draw from. If we didn't draw a caramel the first time, well, then there's still 5 left to choose from. So whether or not the first event occurs affects how likely the second event is to occur. The fact that we drew a caramel the first time makes the next caramel less likely than it would be otherwise. So the fact that we only have a finite number of things to choose from, it's not like spinning a roulette wheel where the numbers are always the same and it just keeps going indefinitely. You can do red, you can do black, and the probability never changes from situation to situation. Because there's only a finite number of pieces here and each draw affects what's going to happen for the next candy you pull out of the box, every single draw is dependent on the previous one or the previous sequence of draws. So any sequence of events in this particular situation is going to be a sequence of dependent events. So all we have to do when we calculate the sequence of probabilities is take into account the effect that the previous events had on the individual event that we're looking at any particular time. So in other words, we need to look individually at the probability for each draw. What's the probability that draw 1 looks the way we're interested in, and what's the probability that draw 2 looks a particular way. So we're interested in the event of choosing 2 caramels in a row. In other words, caramel 1 and then caramel 2. Well, the probability of caramel 1, there's 5 ways to choose a caramel because there's still 20 pieces in the box and 5 are caramels. So 5 ways to choose a caramel out of 20. Now when we go to the second draw, we're assuming that we're drawing a caramel the second time as well. There are only 19 candies left in the box, which means the new denominator for the probability is going to be 19. We're now drawing out of a total of 19. Well, how many caramels are left? We already drew 1, so the first time we had 5 to choose from. We drew 1 the first time, so now there's only 4 to choose from. So after drawing 1 caramel, the probability that we draw a second caramel is going to be 4 out of 19. So the probability that we draw these 2 candies in a row is going to be the product of the individual probabilities. So 1 out of 4 or 5 out of 20 if you didn't reduce it, times the probability of the next one, which is going to be 4 out of 19. Now, if we do reduce it to 1 out of 4 and then multiply by 4 out of 19, we've got that common factor of 4, which can cancel. And so we end up with a probability of 1 out of 19. Now, how could we really prove that these 2 events are dependent? Well, suppose we didn't draw a caramel the first time. What would be the probability of not drawing a caramel? Well, 15 candies in the box are not caramels out of the 20. So the probability of not drawing a caramel the first time would be 15 out of 20. So what would happen for the next draw? Suppose the second thing you draw is supposed to be a caramel. Well, you still have 19 candies in the box, so that doesn't change. But what does change is how many caramels you have to choose from. So if the first candy you drew was not a caramel, that still means you have 5 caramels in the box. So that means the probability of the second draw being a caramel wouldn't be 4 out of 19, it would be 5 out of 19. So this probability of this second event changes based on whether or not the first event happens. That's what dependence means. So if one event doesn't affect how likely the other is to occur, then we know the events are independent. In this situation, one event occurring has the effect on whether or not the other event occurs. Not drawing a caramel makes the second caramel more likely. Drawing a caramel the first time makes the second caramel less likely. So those two events are dependent, and that's what this looks like in this situation. Let's look at another example. You win a free trip to Mexico, and you have the option to take 2 people with you. 10 of your cousins want to go, but only 3 of them actually speak Spanish. If you write their names on slips of paper and draw from a hat, find the probability that you'll choose 2 Spanish speakers. Okay, so think about the sample space. Think about the experiment. The experiment is drawing names from a hat. You have 10 different names in this hat, okay? And the outcomes, the sample space, that's going to be all the individual names you can draw. So there's 10 names to draw from. Only 3 of them actually speak Spanish. So the sequence of events that we're interested in is the sequence where we actually choose 2 Spanish speakers. So 10 names are in the hat. 3 of them actually represent Spanish speakers, but the other 7 don't. So what's the probability that randomly we choose 2 people who actually do speak Spanish? Well, we have to think about the sequence, and then we'll think about independence and dependence as we go. So what's the probability for your first draw that you choose a Spanish speaker? Well, how many ways are there to choose someone who speaks Spanish? There's 3 names in the hat that represent people who speak Spanish, so there's 3 ways to choose someone who speaks Spanish out of a total of 10 names that you can draw from. So the probability of the first Spanish speaker is going to be 3 out of 10. Now, does that affect the second probability? The answer is yes. If you draw 1 Spanish speaker, now you have fewer to draw from the second time. If you don't draw one the first time, you still have the whole group to draw from the second time. So whether or not this first event occurs affects how likely the next event is. So these 2 events are considered to be dependent. Okay, so once you draw one, what's the probability of drawing another? Well, how many do you have to choose from at that point? You've already drawn 1 out of the hat, and so you only have 2 left to choose from. So for your second draw, there's only 2 Spanish speakers left to choose from, out of a new total of 9. So once we draw 1 out of the hat, not only does the total of Spanish speakers reduce, but the overall total reduces as well. So 3 out of 10 for the first draw, and then 2 Spanish speakers out of the 9 people remaining for the second draw. So the sequence is going to have a probability of the product of the individual probabilities. So the probability that we choose 1 Spanish speaker and then another is going to be 3 out of 10 for the first draw, and then 2 out of 9 for the second. We take the product, and that's going to come out to 1 out of 15. So what is that as a decimal? 1 out of 15, approximately 0.07. So about 7% of the time, if you were to draw names randomly based on this descriptive situation, you would draw a sequence of 2 Spanish speakers. Okay, let's look at one more example, and then we're going to talk about this concept of conditional probability. Conditional probability is the second probability. What's the probability that we get a particular outcome based on another outcome already being in occurrence? That's what we'll talk about. Okay, so our last example. 3 people are randomly selected, 1 person at a time, from 5 freshmen, 2 sophomores, and 4 juniors. Find the probability that the first 2 people selected are freshmen, and the third is a junior. In other words, we want to know the probability that we get the sequence, freshman, and then junior. What's the probability that we get that sequence? Go step by step with each individual occurrence. These events, again, are dependent. We have a limited group to choose from, and the first person we choose impacts how likely each of the additional draws or each of the additional choices is going to be, because whether or not that occurs changes how many we then have to choose from out of the group at large. So we're going to go one at a time. So we want to know the probability that we choose a freshman first, and then another freshman second, and then the third person we choose is a junior. Okay. So what's the probability that we choose one freshman to start with? Well, how many do we have to choose from? We have 5 freshmen in the group. How many are there in total? Well, there's 5 freshmen, 2 sophomores, and 4 juniors. So that's going to be a total of 11 people. So 5 freshmen to choose from out of the 11 people in total that we can choose from as a whole. So the probability of our first choice being a freshman is going to be 5 out of 11. So think about the impact on this point. At this point, 1 fewer person in the group, and then also 1 fewer freshman in the group. So now our second choice, what's the likelihood that the second person we choose is a freshman? Well, again, what's the effect after the first choice? The number of people in total has decreased. So that means we now only have 10 left to choose from. Now also, because we chose a freshman the first time, we now have fewer freshmen to choose from the second time. So rather than having 5 to choose from, now we only have 4 to choose from. So the probability of choosing the second freshman is going to be 4 to choose from out of the 10 remaining in total. And then our last choice is a junior. So we've chosen 1 person, we've chosen 2 people, so now there's only 9 people left to choose from. Have we chosen any juniors yet? No, so the number of juniors in the group has not changed. We started with 4, and at this point we still have 4 because our other 2 choices were freshmen. So we have 4 juniors to choose from at this point out of the 9 people remaining in the group. So we take the product of each of those individual probabilities to represent the sequence of events. So 5 out of 11 times 4 out of 10 times 4 out of 9. Of course, you are welcome to do this in your calculator. 5 and 10 reduce, but other than that, you just have to take it all straight across. So multiply your numerators, you'd multiply your denominators, and it comes out to 8 out of 99. What is that going to be as a decimal? 8 divided by 99 comes out to about 0.08. So in other words, about 8% of the time, if you were to choose people randomly from this group, this would be the sequence that you would choose. Okay, so we've looked at a few examples where we have events that are independent. One occurring doesn't affect how likely the other is. And then we just looked at a few examples where our events are dependent. Whether or not one event occurs can either increase or decrease the probability of the next event or sequence of events. So now let's talk about conditional probability. So we're looking at dependent events. Think of events that are dependent on one another. We have to determine the probability of the next event in the sequence given that the first event has occurred, or maybe the third event given that the second event has occurred. In other words, starting at the first event, we don't need to do anything special. But each subsequent event, we have to take into account how the situation has changed based on what has or has not happened at the beginning of the problem. So this probability of an event given that another has occurred is what we call conditional probability. So the probability that event B occurs given that the first event, event A, has already occurred is denoted P of B given A. So the vertical line, we can read that as B given A. So in determining a conditional probability, essentially think of restricting the outcomes to only ones that are associated with what has already happened. In other words, when we look at the denominator for our probability, rather than using a denominator that's representative of the whole sample space of all the choices available, we only look at the choices that are available based on what we know has already happened. So if what's already occurred has then limited our choices, then we take that into account as we calculate the probability of the particular event in question. So think of A as having already occurred. Given that A has occurred means that A has already occurred, A has already happened, so it's then limited what can happen from there on out. What's the probability that the next event occurs given that we're already limited based on what happened in the first step? That's essentially the idea. So let's look at a few examples here. So a letter is randomly selected from the letters of the English alphabet. Find the probability of selecting a vowel given that the outcome is a letter that precedes H. What is a vowel? A, E, I, O, U, sometimes Y. So those are your vowels. Any other letter is called a consonant. So we want the probability that we get a vowel given that we've already chosen letters that precede H. Think of this given that event as being the one that's already occurred. That event has already taken place. In other words, rather than looking at the sample space representative of the entire alphabet, we're only looking at the sample space representative of letters that precede H. So what would that be? That would be A, B, C, D, E, F, G. So 7 in total. We have 7 letters that precede H in the alphabet. So rather than having a denominator of 26, which represents the whole alphabet, our denominator for our probability is only 7 because we know that this particular event has already occurred. We've already chosen a letter that precedes H, so we now only have 7 to choose from because that's the effect of what happened based on the first event occurring. So out of the 7 that represent letters that precede H, we want to know what's the probability of selecting a vowel. Well, based on the fact that we've only picked letters before H, how many ways can we choose a vowel from that restricted group? Well, there's 2 vowels in that group, so A is a vowel and E is a vowel. So out of the limited sample space we now have based on the previous outcome, we have 2 ways for our event, the event of choosing a vowel, to occur. So this conditional probability, the probability that we choose a vowel, given that we've already chose a letter before H in the alphabet, is going to be 2 ways we can do that, out of the 7 from that restricted sample space. That's an example of conditional probability. What changes? Well, it's like doing one of these problems but not looking at the whole sequence. We're not interested in the whole sequence of choices of operations, anything like that. We're just interested in how likely is some subsequent event to occur based on something else, knowing something else has already occurred. That's the idea. Okay, let's look at a couple more examples. So you're dealt 1 card from a 52 card deck. Find the probability of getting a heart given that the card you were dealt is a red card. So in other words, assuming that we already drew a red card, what's the probability that we got a heart? Well, we need to think of the effect of getting a red card. So the preceding event, the given that event, is the card we were dealt as a red card. Well, how many ways are there to get a red card? Well, there's 2 red suits, so there's technically 26 red cards, but let's just think in terms of the suit. There's 2 red suits. We could either have gotten hearts or we could have gotten diamonds. So there's 2 red suits, there's 26 cards represented there. We want to find the probability that we got a heart given that we're only looking at the red cards in the deck. In other words, we've already thrown away the black cards and we've kept the red cards. So we have 2 suits of red cards to choose from, and we want the probability that we're getting a heart out of those 2 suits. So there's 1 way to get a heart out of our 2 suits because one of the 2 suits is hearts. If it helps to think of it in terms of the actual full set of cards in the deck, let's think of it that way. So what's the probability of getting a heart given that the card you drew is a red card? Well, what is that limited to the deck to? How many cards are left in the deck given that the first time we drew red cards? Well, there's only 26 cards left in the deck if the first event is drawing a red card. So there's 26 left to choose from. Well, what's the probability that we get a heart? Well, how many hearts are there to choose from at that point? There's still 13 hearts left in that new smaller pack of cards. So 13 ways to get a heart out of the 26 cards representative of that limited subspace of red cards. So 13 hearts out of the 26 now available to us, which is 0.5. And if we convert that to a fraction, that's going to be 1/2. So our probability of getting a heart, given that we already drew a red card, is going to be 1/2. Does that make the event of getting a heart more likely or less likely? Well, if we were to just draw a heart out of the deck at large, that would be 13 hearts out of 52 cards. What would that be? Well, 13 out of 52 is going to be 0.25, and if we convert that to a fraction, that's going to be 1/4. So if we're looking at the deck as a whole, the likelihood of getting a heart is going to be 1/4. There's 13 ways to get a heart out of 52, which reduces to 1/4. If we've instead restricted the deck to just red cards, now we're twice as likely to know that we've drawn a heart rather than some other card. So that's going to be our conditional probability. Now, what if we flip it? Does that change things? So find the probability of getting a red card given that the card you were dealt is a heart. So now we're going to assume that the first event that occurred was getting a heart. Okay, so how many cards does that now restrict our deck to? So we went from 52 cards to only a selection of hearts, which is going to be 13. Okay, well, assuming that we're just looking at a deck containing hearts, what's the probability that we get a red card? In other words, out of that group of hearts, how many ways do we have to choose a red card? Well, this seems kind of a weird question, because think about it. If we've restricted everything to just hearts, all of the hearts are red cards. So out of the 13 hearts, 13 of them are red cards. All 13 out of the 13 we have to choose from. Well, 13 out of 13, that's going to be 1. So in other words, if the preceding event is the fact that we've dealt a heart, then it's actually guaranteed that we'll get a red card. Now, if we were again looking at the whole deck, what's the probability of getting a red card? At that point, the probability is 1/2. Half the time we'll get a red card, half the time we'll get a black card on average. If we've already restricted the deck to just a selection of hearts, then we are guaranteed to be choosing a red card, because all 13 cards out of the 13 hearts are going to be red cards. So having this conditional probability, the probability conditional on something else having already happened, does change whether or not that event is likely to happen or whether it's unlikely to happen, just based on the fact that these two events are dependent. Now, if the two events are independent, then conditional probability doesn't change anything. So for instance, what's the probability of rolling a 1 on a die given that you rolled a 2 before that? Well, the probability doesn't change. If you roll a 2 before that, that has no impact on rolling a 1 the next time. Those events are independent. So conditional probability is really only something we have to consider in situations where the sequence of events represent dependent events. One affects the other, and it either increases or decreases the likelihood. Now let's revisit that table we had with marital status. So we looked at this in the last section. Let's look at this again, and let's put this in the context of conditional probability. So recall that we have marital status in the columns, we have binary gender in the rows, out of a total of 254 million. Okay, so we looked at one event or another occurring based on how people are categorized in this table. What about conditional probability? What would that look like in tabular form? So if one person is randomly selected, we want to find these particular probabilities. So the first probability is that we get a person who's female, given that the person is married. In other words, we're going to assume that rather than looking at the whole table, we're only looking at people who are married. So we've restricted the sample space of 254 or 254 million to only the individuals representative of what happens once we allow that first event to occur. In other words, we're only looking at the married people rather than the whole group of 254 million. We're restricting our sample space to this smaller subset within the set of the sample space as a whole. So first thing, the person is married. In other words, we're only looking at the column of married people. Given that the person is married means we're only looking at the column of married people, which has a total of 133. That total is now going to be the denominator for our probability. So what's changed every time is the denominator. We're looking at just that particular subset within the sample space. So we want to know what's the probability that we choose a person who's female, given that we're now restricted to the category of married people. Well, how many ways can we choose someone who's female if we're restricted to the category of married people? Well, there's 67 people who are female. So there's 67 ways to choose a person who's female, given that we're restricted to the category of married people. So our probability is going to be 67 out of 133, which is approximately 0.5, so about half the time. Notice it's split almost evenly, 66 and 67, for a total of 133. So the probability about half the time, if we're restricted to the group of married people, about half the time we're going to choose someone who's female. Now, what if we flip this? So what's the probability that the person is married given that the person is female? So now we're assuming that the opposite event has happened first. So rather than restricting us to the group of married people, now we're restricted to the group of people who are female. So the group of people who are female, there's a total of 131 million people in that group. So rather than looking at the group of 254 million, we're now restricted to the group of people who are female. So given that the person is female already, so out of the 131 million. The event we're interested in is the person is married, given that they were already female. Well, given that we're looking at the category of females, how many people are married? Well, out of that group, there was 67. So notice the numerator is not going to change. We're still looking at the same intersection, the intersection of people who are married and people who are female. What changes is the denominator, because now, rather than assuming they were married to start with, we're assuming that they were female to start with. So 67 people within that group, but now it's out of the 131 million that represent that first event, the event that we choose someone who's female. So 67 out of 131. Notice the denominator is now lower, which means this fraction is bigger. So that's approximately 0.51. So this conditional probability is slightly higher because we now have a lower denominator. We're choosing from a smaller group, so 67 is a larger fraction of 131 than it is of 133. Okay, let's look at a couple more. So what's the probability that the person is male given that the person is divorced? So let's see if I can fit it. That'll work. Okay, so we can see the table and we can see both of the examples. So the probability that the person is male given that the person is divorced. So given that means this event, we chose a person who is divorced, that event has already occurred. So instead of looking at the 254 people in the whole group, we're now restricted to the category of people who are divorced, which has a total of 26 million people in that category. So based on being restricted to that category, what's the probability that we choose a person who is male? Well, out of the category of people who are divorced, 11 million out of that group are male. So there's 11 ways to choose someone out of that group, given that we're now restricted to this group of 26 people. So 11 out of 26, which comes out to approximately 0.42. Now let's flip this one. So what's the probability that the person is divorced given that the person is male? So now we're assuming we started by choosing someone who's male, so restricted to the group of people that are male, which gives us a total of 123 million to choose from. Well, out of that group of 123 million, how many ways do we have to choose someone who's divorced? Well, out of the group of 123 million, 11 out of those are divorced. So now we have a probability of 11 out of 123. Again, notice that the numerator hasn't changed. What does the numerator represent? The numerator represents the intersection of these two events. It represents whatever region in this table represents both of those events occurring at the same time. So male and divorced, divorced and male. Male and divorced, divorced and male, that means the same thing. The only thing that's changing is how we're restricting our sample space. So in the first situation, we're restricting it to the category of people who are divorced, and there's 26 in total that are divorced. In the second one, we're restricting ourselves to the category of people who are male, and in total there are 123 people who are male. But the numerator is the same because the numerator just represents how many people fit under both categories, and that doesn't change by changing the order that we look at the events in. So 11 out of 26 if we're restricted to people who are divorced, and then 11 out of 123 if we're restricting to the group of people who are male. So notice there's a significant difference in those two probabilities. So conditional probability, the order we put the events in does change things. The order we put them in tells us how we're restricting the sample space. Based on how we're restricting the sample space, we end up with pretty significantly different probabilities.